Tonight we are continuing our lesson on fluids and pressure. We're starting with atmospheric pressure, or otherwise known as air pressure. Air is a fluid, okay, because it's a gas, air is a fluid, and air has weight. That means the weight of the atmosphere is pushing down on you and everything else. Okay, we have about 62 miles of air above us. And that air, although a little bit of air doesn't weigh much, 62 miles of air does weigh quite a bit of us, and that's all pushing down on us and everything else. At sea level, the normal atmospheric pressure is 101,300 newtons on every square meter. So what's the atmospheric pressure in pascals? Okay, kind of a tricky question, or maybe not a tricky question. It's kind of a fool question. A pascal, remember, from last chapter, or last section, is a newton per meter squared. Okay, so if we have 101,300 newtons on every square meter, the pressure is just the same, 101,300 pascals. Okay, so I didn't change anything, just kind of a tricky little question. It's just getting you to realize again that a pascal is a newton per meter squared. Okay. In earth science, we usually don't talk about pressure in this terms of pascals when we talk about atmospheric pressure. We're actually going to talk about it in millibars. When we get to the weather unit, we're going to be talking about millibars, and it's actually 1,013 millibars. Okay, and that's what we're going to be using a lot more often when we get to the weather unit. And if you look at the weather station on the side of the room, you'll see that it's in millibars, not in pascals. Okay, so either way, we have lots of air pushing down on us. Okay, that 62 miles of air is about 10 newtons, or about 2 pounds, on every square centimeter of your body. If you want it in square inches, it's about 14.7 pounds per square inch. Okay, so why don't we feel it? Okay, if you're standing there, why don't you feel that 62 pounds, or 62 miles of air pushing down on you? Okay, how can he hold his hand up? Okay, so lots of questions in there. First thing is, how can he hold his arm up? Is because pressure, the air is flowing everywhere. It's not just pushing down on his arm, it's also pushing up on his arm. Okay, it's pushing every direction. So that's why you can raise your hands or lift up your hands. The pressure is going in all directions. It's coming in the room, it's seeping underneath the doors, through the cracks in the window. Air pressure is seeping in everywhere, pushing equally in all directions. Now the question of why don't we feel it? Okay, well that's a little bit harder one. Okay. We don't feel it. Kind of the answer is because we're used to it. We have internal fluids in our body that push out equally. Okay, not the same as Newton's third law. Okay, don't think of this as Newton's third law. We have internal fluids that are pushing out equally, that equally balance with the pressure. Again, I said it's not Newton's third law because our fluids push out at whatever it is, all right, kind of at this 14.7 pounds per square inch, that's 10 newtons on every centimeter. So if I go up in altitude where there's less air pressure, all right, I don't feel right. My body's still pushing out the same. Or if I go diving underwater and now I have the water pressure pushing on me, my body doesn't push out anymore to combat it, and we can feel it. Okay, if I would go into space, okay, all my little blood vessels and everything would be popping, they'd be all rupturing, because my body is still pushing out with all that pressure. Okay, so it's not Newton's third law, it's not equal and opposite, it's just our body pushes out, our internal fluids push out with about this 10 newtons on every square centimeter. Okay. I'm going to show you the atmosphere bar in class. It's just an iron bar that represents the weight on every square inch of your body. So it's a long bar, and you can feel that pressure, okay, that 2 pounds on every square centimeter. If you kind of think of the math, an average person, you have about 20 tons of pressure trying to squish you. Okay, so we have about 20 tons, over 40,000 pounds of force trying to squish us. And luckily we have our internal fluids that push out and keep us from getting squished. Okay. Okay? Again, not so if you go into space or something like that, our fluids push out more. Or if you go underwater, they don't push out enough. We're going to talk more about atmospheric pressure when we get to weather unit, as I said, but notice that the pressure of the atmosphere decreases with altitude. Okay, so here's the bottom layer of the atmosphere, the troposphere, okay, and there's the pressure, and you see it's measured in millibars. As I said, it would be. Normal is 1,013. Okay. The pressure is a lot higher lower in the atmosphere. As you rise in the atmosphere, the pressure decreases. Why? Okay. Remember, atmospheric pressure is the amount of air above pushing down. So if you're way down here in the troposphere, you have lots and lots and lots and lots and lots and lots and lots of air pushing down on you. So it's high pressure. When you are up here, you don't have very much air pushing down. Okay, so the deeper you go, the higher the pressure. Also notice, kind of in this picture, that down at the surface the air molecules are really, really close together, and as you rise up in altitude, the air molecules are spread farther and farther apart. That's again because of this. Okay, the higher up, there's less pressure pushing down, pushing these molecules together, so they're not as close. They are free to kind of spread out. But down near the surface, there's lots of pressure, and it's forcing all these molecules really, really close together, so they're a lot denser. So why do your ears pop with altitude change? And I just copied this from a web page that explains it, but I'm going to kind of try to explain it here. And if we look at this picture, you see kind of what your inner ear looks like. So this circular section here goes here. You have your eardrum here, and notice that there's a little gap, okay, right up above your eardrum. Okay, that air can go in and out. So then you have your inner ear here, and then just the outside air here. So if you are down on the surface and you're having a good time down here, okay, at the bottom of a mountain, okay, and you're yawning, you're talking, you're moving your jaw, so this gap opens up and the air pressure is equal. Okay, so inside your ear and outside it's equal. But then if you start to climb the mountain, okay, as you go up, what happens to the pressure outside? Okay, remember there's lots of pressure pushing down here, but less pressure here. Okay, so there's lower pressure outside your ear, but the pressure inside your ear is still high because it was trapped by your eardrum. So you feel like your ears are going to pop. Okay, are they popping in or out? Okay, they're going to pop out. So you move your jaw, you try to get this gap to open so that high pressure can seep out through that gap, so your ears are going to pop from high to low out. Okay, so you do that, your ears pop, and you're all happy now because your ears popped and it's not hurting. So then you start climbing down the mountain. Okay? So as you climb down the mountain, your ears start hurting again. Okay? Because you had low pressure trapped inside your head, but now there's high pressure outside. That high pressure tries to get into the low, okay? So it tries to pop your eardrums in, okay? And it'll go the other way. And you can read this here, but I just like this. I put it on here. It said, never hold your nose and blow to clear ears. If your throat is infected, you'll blow that infectious mucus into your inner ear. Instead, swallow hard several times to wipe clear the opening of the eustachian tube. And immediately yawn and stretch your jaw forward and repeat efforts to open the tube to release the pressure. Okay. When you're scuba diving, they do teach you to hold your nose and blow. Okay. That's because water is a lot more dense and you can rupture your eardrum a lot easier, so it's worth the risk of getting an infection because you don't want to have your eardrum rupture. Okay. We're talking about water pressure here really quickly. Why does water pressure increase with depth? Well, same exact reason, okay? The deeper you are, the more water is above pushing down. Why does water exert more pressure than air? Because water is more dense than air. Okay, water is over 1,000 times more dense than air. Density is just the mass per unit volume of a substance, and we're not talking about this. We're going to have a lesson. Our next lesson is actually going to be just on density, so we'll talk about density then. Okay, so pressure and fluid flow. When you drink through a straw, you are not actually sucking the drink through the straw and into your mouth. Okay? So let's just look at this example. So here's the water, and here's you, and you're going to suck the water into your mouth. Okay, when you suck on the straw, you're removing the air from the straw. That makes low pressure. Okay? It's high pressure outside. Okay? The high pressure tries to get right to the low, but it can't because the straw is too strong. So that high pressure pushes the water up the straw and into your mouth. Okay, and that's how you drink. It's just high to low pressure. Maybe you've had a really, really, really thick milkshake. Okay, and you suck in that straw and you suck and suck and suck and suck, and the milkshake is so strong that eventually the pressure difference gets too great and the high pressure just goes bam. I'm getting to that low pressure and it crunches the straw shut. Okay, it's the high pressure getting to that low pressure. And we're going to do some different labs with that. But again, the key thing, and I mentioned this before, fluids always flow from areas of high pressure to areas of low pressure. You might have done a little experiment, maybe not experiment, a little fun, where you go to McDonald's and you have your soda and you have your little brother and he's annoying you. So you take your straw and you get some soda in it and you put your finger on top of it and you hold it there and then you lift it over your little brother and it has the soda in there and has your finger on top and you, I'm going to drop it on you. Okay, but it's held there because you have low pressure in here and the high pressure is holding, I should have had the soda in there, the high pressure is holding the soda up. Okay, what happens if you remove your finger? Then of course the high pressure can go in that way and the soda falls on your little brother and you get in trouble. Okay, another couple examples of this fluid motion. Breathing, same kind of thing. You have your diaphragm here. If your diaphragm goes up, it's going to squeeze your lungs, all right, making high pressure, lots of air in a little area. Lower pressure outside, so you exhale. Breathe out high to low. If your diaphragm goes down, your lungs expand, making lower pressure here, higher pressure outside, so you're breathing in. Weather is the same kind of thing. We talked about it with the hurricane unit. If we have low pressure, okay, so let's start with this one with low pressure, the air from high pressure goes into low. The low pressure rises, usually because it's hotter. We'll talk about that with weather, and it makes clouds and rain. If the air is descending, it's making high pressure. High pressure is then going to go out to low pressure. Okay? This movement of air from high pressure areas to low pressure areas is called wind. So whenever you see a weather map, this is what you see. The high pressure, the air is descending. The low pressure, the air is rising. And then wind tries to go from high to low. Now it has to turn because of Coriolis effect, like with the hurricanes. And we'll go into this when we talk about weather. Okay. And that's it for today. Remember, high to low. Okay, fluids always flow from high to low. Atmospheric pressure is the weight of air above, pushing down. And we're going to talk about density in the next section.